Hey guys, I'm going to be doing a file analysis for Rumble Roses XX, and just dealing with their object or model format. They call it the Y object, probably for Ukes object or something like that. Their file extension and the file identifier is called OBJ. Probably abbreviation for use object. If you're interested in the structures for whatever reason for your coding, you're going to code your own or something like that. Hopefully, I'll get a chance to write it in a Excel file, and I'll put that on my Google Drive so you can access that. It'll be public. All right. This video is going to mainly be for people that kind of want to get more of a a verbal understanding of the structure. Someone who just wants to, maybe mod the game and has little experience with programming, they can kind of look at this. And hex editing is pretty much a straightforward thing. You have a number, you change it, kind of thing. So you just got to understand how to follow structures and do away with whatever you're planning to do. Anyway, so let's get going. Basically, the Ukes binary format here is constructed of chunks. So we see a chunk descriptor that describes a chunk. Okay, so these first 4 bytes here are the chunk descriptor. It defines 2 variables here. The first one is a 4-byte character code, which if you swap it around, it spells Y object. Okay. After that, you get the size of the chunk. All right. So this is your chunk header, your chunk descriptor, or whatever you want to call it. So after this is the chunk. So it's basically, I guess, 3 parts. So you got ID, size, then the chunk itself. All right. So if we take the chunk size, all right, and I push past the beginning of the chunk, so I address past here, this position, it'll bring us to the end of the chunk, obviously, and on to the next chunk, which this chunk is called. I swap around. It is called 0 fop. So I kind of tried to imagine what 0 fop could mean. 0 file operation parameters. I'm not 100% sure really what it stands for, but the data here is the reason why I'm unable to write new geometry. And the patterns that we see here correlate to patterns that we see in the first chunk. So this obviously piggybacks off the data that gets defined in the upper file, which is the actual model. So the reason why we can't write new geometry is because if we change the geometry up there, we have to rewrite this second chunk, and if it's not done properly, the game just falls through, doesn't pass the model. So yeah, this is the problem, and I'll cover this at the very end of the video. It'll probably make more sense than it would right now. All right, so let's go back up and we'll cover the first chunk. All right, so again, this is a chunk descriptor. So your actual chunk begins here. So any addresses that are defined within the chunk are going to be relative to this point. So this is in hex, it's 08. So if we had an address, you would have to jump that address from this relative point. Okay. So to simplify this for everyone, I'm going to delete the first 8 bytes, so that when we're working within this chunk, all the offsets are, well, they're relative. Okay. So, hello. This is the Ukes object format here. So it begins off with a typical header, all right, and then followed by some tables, actually a lot of tables, and then there's some buffers in between and stuff like that. So that's the overall format. So let's follow the header structure here, and I'm mostly going off the top of my head, so let me just bring my notes in case I get a brain fart. So this first long integer value. Oh, which by the way, this entire file is it's an Xbox 360 file, so of course it's going to be big endian. However, there is about 2 spots in the file that is going to be little endian, but I'll tell you about that. So you can consider this all big endian. Okay. Okay. So sorry. So let's begin then. So the Uke's object begins with this long integer value. It's unknown because it's always 0, so it's a constant, but I'm not sure what it describes, so it's unknown. My phone went dingity dong. Okay, what the fuck? Alright, so after that we have the address for the second chunk. So that's kind of curious why they include that, but obviously it's an important part. So if we offset to that position, there we are, the second chunk. Next is 2 more unknowns, just because they're always 0. I have no idea what they are. This one is the sub-object count. So the model file here is describing one model, so you're going to import one model, and that one model will be made out of sub-objects that collect together to form that single object. All right. So we have that, and then we have the address to the sub-object table. So that'll describe the table. That table will describe every object, be it how many vertices and yada yada yada. Okay, so that's the address. So that begins actually here. Right, next is the number of bones in our skeleton, so we have 114. Next is the texture table count. So your materials can, reference the same material a couple times. So to save on, size and redundancy, you create a unique texture table so that your materials just reference to the table. So if it wants texture 2 in the table, it says 2. Excuse me. Holy crap. Alright, so that's your texture count. Next is a couple offsets. So the first offset would be, I think that's your skeleton. The second one is your texture table, yeah, and then the third one is your object name table. Alright, so let's go to the texture name table. Okay. So this is the texture name table. Now this is a recent discovery. I was hexing and I was modding, and then I realized this. So yeah, so each entry would be 16 bytes long, obviously, and they would contain a string for a texture name. All right. There's no extension, so the game typically uses DDS. So you'd have to add .dds as the file type to assign it a texture name. However, anyway, the one thing I was confused about was I just had assumed that each string was going to be 16 bytes or 16 characters long, and the rest of the space was reserved, right? That turned out not to be true. Actually, only 12 of those bytes are reserved for the actual string, and then the last 4 seem to be open for some type of parameter, which is weird. Okay, so if we look here on this one down here, this is the longest name that we can see in the table, so that's 12 characters or 12 bytes. And then after that we have a big endian, long integer value, I mean, and it just says 13. I don't even know what that means, and it's on 2 of these textures. All right, so this is not known. I have no idea what it is. I would assume it's a parameter. So if you have a texture and you need transparency or something like that, or if it's a volume texture or it has bitmaps, maybe it's something like that. So yeah, I'm not sure what this value is, but yeah, your character space is actually 12, not 16. And that's what I found out. Right. So yeah, those are your texture names, and then we go back up to our object table or our header. Sorry. I'm gonna go back up. Okay. So now that we've clarified that, let's just jump to this object name table. Now, to my understanding, there's only one object you're building, right? So this count that comes after it, which is 1, I just kind of associate that it's the object count, which would be 1. So I have that like thing in my head. Okay, can you have 2 objects? Like, holy shit, can there be 2 objects? But I'm actually not sure. This is unknown. It's described as unknown. I don't know what it is. But anyway, this is pretty self-explanatory. So let's follow this offset. That gives us to this address. So again, similar to the texture name table, we get a name that would be applied to the object. So based on the stuff we witnessed in the texture name table, I now have to assume that the structure is probably similar for the object name table. So we're going to be reserving 12 characters for the namespace, followed by probably a long integer value for some type of flagging information. Now this part is a little bit confusing because we have 16 extra more bytes. So I'm not sure if it's a part of the table or if it's a separate piece of data. Now the interesting thing is it defines 1. So what does that mean? 1 what? And then it defines a count. So maybe it's saying, okay, we have 1 object, and this is how many things are in that object. So I'm kind of wondering what this all is, but I think it may have to relate to the FOP data section, the second chunk of data here. This count is actually directly related to the sub-object count. Actually, it's identical to the sub-object count. And we see that the stuff in the second chunk is looping for the sub-object count. So for every sub-object, there is extra data in here. So yeah, not sure exactly what that is, but that is the sub-object count, and it's stated twice. All right, let's go back up. Now, the last thing, I danced around. This offset here is actually the skeleton, so that's bone entries, right? So let's hop over to there, and I'll pick apart that. So let me just expand the columns so that we can get the definition here for each bone in a nice column. Come on. You know, I actually just remember. I think it's 80. I hope it's 80. Yeah, here it goes, 80. Okay, so each bone entry is 80 bytes long. Where does it begin? Here it is. Again, I'm just going to cut this off just for simplicity so that it can be easily seen here. So yeah, this is the beginning of the bone entries for the skeleton table. So each 80 bytes is going to be 1 entry or 1 bone. So this is the root bone. Okay, so looking at the ASCII here, you can see, yeah, that's string and then the rest of it's bytes. So let's go over to the byte view. So yeah, so this is going to be most likely, again, reserved character space for, it's probably 12 characters again, reserved, followed by another, flag. So long integer value for a flag. Then after that we have these presumably 4 float values, and it would consist of X, Y, Z, W. So the W component mostly is usually a scalar value, but they wrote 0, which means it's not that. So it's not really known what this is. It's unknown. But this is X, Y, Z position data for your skeleton. All right. And then after that, we have the X, Y, Z rotation values. These are defined as, what is it, radians or radians? Rads? I forget what it's called. I'm not a mathematician, but yeah, those are rads. So you have to convert them from rads to degrees, which I think is the value times pi divided by 180. I can't remember. There's the formula on there for converting from rads to degrees. But yeah, that's what this is. It's rads. Is it rations or radins? Radins? Oh fuck, I forget. So yeah, you take these, you convert them to degrees, and then you get X, Y, Z degrees. I plugged mine in as earlier angles into 3ds Max, and that worked out. Then you have that 4th component. Okay, you can just skip that. That's unknown. Next, we have the parent information. So which bone is this bone linked to, kind of thing. So this information is important because you need to read this in order to unpack the skeleton. The positions are all relative to their parent positions. So typically you would have to read the parent information. So this is saying it's connected to bone 1. So you have to go to bone 1, take the current matrix for that bone, multiply it by the bone that it's child to, and then you unpack it that way. So yeah. Anyway, so after that we have 3 more long integers, which are all zeros. They're unknown. I have no idea what they do. All right. And then the last bit here is a little curious. This is the only section. There's another section, but this is one of them, which is not defined as big endian. It's actually little endian. So it's a little change up. So it's defined as x, y, z position. It's actually the center of the bone. So yeah, so it's the center of the bone. It's defined in little endian. So you have x, y, and z. And then the fourth value here is the distance from the center to the origin. Again, that's little endian, so that's kind of weird. Okay, and so yeah, that loops over for the bone count, and there you go. That's 1 entry for a bone. So let me just bring this back to its original state here. All right, so let's head back up top here. All right, so we ended up at this unknown value. There's another row of zeros for them, or 4 long integer values. Yeah, I don't know what those are. Those are either null, like padding, or there's something that is constantly 0, so I have no idea. And now we're at this address, which is the beginning of the sub-object table. Okay, so each sub-object entry is going to be, what is it, 180 bytes. Which in hex is, I think it's like 8B4. That sounds familiar. Yeah, it's B4. All right. So the first long integer value here is the vertex count. Now you notice something interesting about the vertex count for each one of the sub-objects. You'll notice they won't exceed 512 vertices. Which, if you think about it, this is probably what they did. Usually when you cut up a model to export it to a binary file, what you do is you separate the materials. So you have one single model, but you have to separate it by material, and then you separate those as sub-objects. So each material is a sub-object at that point. In this case, they don't treat each material as a sub-object. Well, they do, but what they did is, let's say they take one sub-object, and that's one material, right? So they take something like that. But the vertex count exceeds 512, and they're like, oh no, you can't do that. So they chopped it up into like 50 parts, and so they made it so that one material fits into vertice chunks of 512. So you bloat up, you're bloating your file basically. So they're going from one sub-object that's one material, and they're cutting it up 50 times to meet a requirement where they can put it into vertex chunks of 512. So this just kind of blew my mind, because I'm like, wow. Like, I knew their format looked a little sloppy, but this is dumb. So I'm like, wow, dumb. Anyway, so yeah. Oh, I'm sorry, Michi. Where am I right now? So this is the vertex count, right? After the vertex count, we're given the strip count. So that's how many triangle strips are included in the sub-object. Okay. After that, we have the bones that are used. So instead of it's basically telling you how many bones influence this sub-object. Because you could have a skeleton with 1,000 bones, but maybe only 5 of those bones are influencing your object. So this is also used in the vertex definition when it does a weight lookup. So it's not your weight values and your bone indices aren't. They're not looking at the skeleton. They're indexing to this table here. So they're relative to this. This, I guess you could call it bone table, I suppose. Okay. So we're given the count 7, and then you would loop 7 times. So 1, 2, 3, 4, 5, 6, 7, and then the rest of the tables padded out. So, or reserved, I guess. So it reserves 20 long integer values. So really, they're wasting a lot of space because they store a long integer value, and instead of storing a byte, when they're only reserving 20, which is a lower value. So anyway, so you can skip ahead 20 times 4 to get past that bone table. And then we got this value here, which is the bone influences. So that means if you have one vertex, how many bones are influencing that at any given time, right? So it'll be 3. So that, I don't know. It's kind of self-explanatory. After that, we have another unknown. This is like a constant. Actually, let me just check my notes. Make sure I'm not feeding you bullshit here. Where am I? Weight offset. Oh, yeah, okay, sorry, I was mistaken. Right after the weight influence count here, this is actually the material ID. Okay, so this is using material 1, right? So if we were to skip current position before, so that one's the same material, this one's the same material, this one's the same material, same material, same material, same material. Material. Wow, they're like all the same material. Okay, I goofed up somewhere. Anyway, so yeah. Whoa, I got totally lost. I'm in a different file. Holy shit. Fucker. Alright, so, yeah, wait, let me just confirm that. Is that the, shit. And the holy crap, number of bone weights. Okay, yeah. This is material ID, even though I didn't really see it change. But yeah, that's the material ID. And then after that, this is a constant unknown. It's always 1 that we don't know. But yeah, this is the material ID. Okay. Anyway, so where was I going with that? Okay, so that's constant. Then this is a offset. This offset is the the vertex offset. So this is where it gets interesting now. So now we're starting to understand the structure. So let's offset to the vertex buffer. What did I just do? Oh, that'd be why. Okay, that brings me here, and this is just a single long integer value, and this is another address. So you just copy that address, and you jump to that address, and that is where the vertex buffer is. And oh, it's right beside it. That's messed up. So yeah, that's kind of stupid. They give a address in the sub-object information, and then they offset to another table, which gives you another address to the buffer, which is right beside the table, which the table is always just holding 1. So yeah. Actually, you know what? That's probably what the count means. Now that I think about it. Yeah. There's a count up here. This thing. Where am I? Yeah. Yeah, this count that's right here. It probably means the number of sub-buffers, or vertex buffers, which is always going to be 1, right? That makes sense. And then you have 1. Okay. I'm going to put that in my notes. Give me a sec. Give me a sec. So this is always 1. That's because it is the vertex buffer count. This is the vertex buffer table. Okay. Sweet. Progress, man. Progress. Okay, so that is... Alright, so that's the table, which is 1. Then that brings us here. Groovy. Alright, so from there, this seems to be like the same standard vertex setup. So I haven't seen anything different, but yeah, it's broken up like this. So you get X, Y, Z as a big Indian float. So that's X, Y, Z for position. And then again, you have X, Y, Z, but for the vertex normal. So that's X, Y, Z vector. And then after that, you get these FFS. Typically, you would assume that just means a terminator. They're just filling it with zeros because they're not using it. But I kind of think that it might be vertex color information. However, that might be not true. So I'm not sure what that is. And that's it. Then it goes to the next vertex entry and so forth. Okay. Let's go back to our object table then. sub-object table. All right, so that was the vertex buffer. Oh, excuse me. Okay, and then we have the weight buffer. So it has a bunch of vertex weights in it. So let me show you that. Now keep in mind the influence count here is 3, so that's important. So this is actually, each entry is going to be 8 bytes. Let me just shrink the columns here. Oops. So that we can get a better representation of that. Where am I? Okay. So yeah, each one of these is going to loop over per the bone influence count. So ours was 3, right? So this is defining 3. So 1, 2, 3. And so if the influence count was 4, you're obviously going to read 4. So 1, 2, 3, 4 before you go to the next vertex. So this set of 3 is the first vertex. This set of 3 is the second vertex. And the third set is the third vertex. Okay, get it? So yeah, so each entry here is broken up into two parts. So we have bone index. All right. From what I can tell, it's just 1 byte, and then it's padded to 3, because you can see here the terminator value doesn't terminate the whole long value; it just terminates this byte. So I believe it's just a byte, and then it pads off with 3 bytes, and then you're given a big endian float value. That's the weight. So obviously these 3 have to add up to 1. So you can see here in the interpreter, it's going to be 0.091 blah blah blah, and the other value is oops, it's what is this thing? Oh, it's 0.0892. It adds up to 1 pretty much, and then this one's 0, and because it's 0, the bone index is -1, so it's putting a null character here. Okay, so these indices here, let's say for example this one says 1, right? So you have to go back to your what do you call it? The sub-object table. 1 would be this indice or index, bone index rather, in your bone table, because that's 0 in your array, and this is 1 in your array. So 1 will actually be that one, right? And that's reading 38. So you go to your skeleton, which is here. All right, that address. This is your skeleton information. So I forget what that was. It was like 38. So the 39th one would be the 38th one in your array. So that's the bone that you would assign that influence to. Okay, just to make that clear. So anyway, where are we at now? Dummy, where am I? Here, yeah. Okay, so this one here, this is the offset to the texture coordinates. So if we follow that, this one's real simple, and this one's just 2 float values, obviously. So your U and your V, so your texture coordinates, UV. So that's your first UV, your second UV vertex, or whatever, and so forth and so forth. So that one's very easy. Okay. Let's go back up to my sub-object thing. All right, now this one's your count. Again, I don't know. This count is actually directing to. It's always constant. It's always 1, and then we're given a string value. So again, I assume it follows the same structure. So it reserves 12, and then gives a long integer value for some type of flag information. So this is the actual name of the material. All right, and so this is duplicated, obviously, because the way Ukes did it, they took one sub-object or material and they cut it up based on vertex limiting. So yeah, that's your material name. Okay, so you can either do a lookup with the ID or do a lookup with the bone name, or not the bone name, the material name. I would suggest doing it with the ID. That's what I did, and then you can apply the material names later. All right, next is 2 unknowns. I believe this has some correlation with the second chunk of data, but it must serve some purpose, obviously, with the main chunk. But 6 and 6, I don't think it has any relevance with the data anyway. Anyway, carrying on, we're given this count 14. This is the number of material parameters. So it's interesting how they did the materials, and I'll show you in a sec. So this is the address for the materials. Keep in mind we have 14 parameters. So let's go to the offset or the address for the materials. Okay, so this is the material parameter offset table, I guess you could call it. So it's going to give you to this table, and when you follow each offset, it'll bring you to this string down here. So this is the first parameter, all right? So you're going to loop through these for whatever the parameter count was, obviously, and you follow these offsets, and they just bring you to these strings, okay? So these are parameters. So you read this parameter, and this is like, it's kind of self-explanatory. Material, diffuse color, specular color, specular level, specular power, yada, 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 yada. Okay. So for each parameter, it defines something. So after each parameter, like the string here, so we would read 16 bytes, like a character space of 16, and then you're given data. So this one would say, I don't know, it's given 13, 36, a float value, another float value. So I actually haven't worked too much on this, so I don't know too much about the parameters for materials. The only thing I looked at in terms of the parameters is the diffuse texture parameter down here. So this one it's pretty simple. So you'd read a 16 character space, and you're given some data. The first two short values are unknown. I don't know what they do. And then you're given a index, a long integer index number, which indexes directly to the texture name table, which we saw earlier in the beginning of the video. So yeah, this is well understood, fairly much. The rest of the stuff I actually haven't gone through, because every time you pass a parameter, you have to pass a custom structure, like a, because each one of these has an individual structure to follow, right? They're not all the same. Like this one gives two shorts and a long. However, if I go to this one, it gives me like 4 floats or something like that. So based on the type of parameter, you have to read the data differently. And that I do not have documented. The thing is, you might come across a parameter that's not supported, or I don't know. It's it was a headache for me to look at. So I looked at the texture diffuse parameters so I could get the basic mapping applied. So yeah, that's the material data. Okay, interesting how they did that, by the way. Okay, let's go back up to our table. We're almost done, by the way. So after the material table, we have, actually I kind of forget what this is. Oh, I remember. This is the strip table, the triangle strip table. Now this is weird, actually. I've never seen this before. Let me just cut this so it's square. So yeah, I think I described this already, but a triangle strip is, when they try to optimize, and instead of describing a triangle per triangle, you describe it. If a triangle shares an edge, they can just define it as a single strip, right? So for each one of those strips that they were able to optimize out, they have an offset to each of the strips. So instead of just putting a Terminator character, which is usually just FF to reset the strip, they physically give full control over it. So they put the start and stop of it basically right here, which again is costly on memory, which is it doesn't make any sense. Anyway, so we see this this first integer here. It's 6. I have no idea why they use 6. They really like using the integer 6 for some reason. I would assume it's a type of parameter, basically saying, okay, this is a type 6 triangle, which probably means the strip. If it's maybe a different type, like a type 0, maybe it's a triangle list or something, a different type of primitive type. That I don't know. It's always 6. It's a constant, so I just left it at that. This is your face count, so how many faces are defined, and then this is the offset to face. So pretty simply, you just you follow the. I deleted one of the bytes. Okay, so you just follow the address. All right, and then you follow the number of faces. So that one was 20 in hex, so that means 32 faces. Each face is defined as a short, so times that by 2, 64. Convert dec to hex is about 40, right? So we go 40. And that brings us here, so that's this is the first strip here, okay? And we know that because the second address for the second strip brings us here. Oops, went too quick. So yeah, that's where the second address goes to. So that's the first strip, okay? And like I said, usually they just type a FF value here, so that when you're reading along and you hit an FF, you're like, oh, I'm out of range, so I must be a terminated value. So they terminate the strip and they start a new strip. So what they did is kind of ass backwards, to be honest. So yeah, let's go back up to our sub-object table. I think we're done, actually. No, actually, there's another piece to it. So yeah, we're almost done. So that was like the last offset, and then we have another count. You'll notice that this count matches precisely with the vertex count. So I'm not exactly sure what this count means. It could be the texture coordinate count, weight count. It's up to interpretation why they duplicate the count. I have no idea. So yeah, that's the vertex count followed by a unknown. Okay, that's always 0. It's constant. I'm not sure what it is. Maybe it's padding. Then we have that funky thing that we saw on the bones. So this is going to be little endian now. So this is little endian. It's x, y, z position of the center of the object, and then this value is the distance from that center to the origin. All right, and then that's it. That's the entire definition of the. So if I highlight it, it should be what is it? 4B, which is 180 bytes. Yep, that's it. That's the entire sub-object definition. Okay, and that completes the format, obviously. Other things you could add, obviously. Well, I was going to mention the other data section, but just give an overview of how that all kind of works. So yeah, these are defined as sub-objects, but because they broke up a single material object into multiple objects to meet a requirement of a specific vertex count, like this thing, right? This is 512, right? And so if we skip to the next entry, it's same vertex count, 512, 512, 361, 512, 162. So yeah, every time their object exceeds 512, they break it up until it fits in chunks of 512. I think I mentioned that, but maybe not. So yeah, so that's why one material object gets split up into maybe a dozen or more. So so what I did is I read all the entries in this sub-object table, and then I had to sort them so that I was only dealing with the first material, second material object, third material object, and I constructed them by material, and then I constructed that as a single object. So for me, it was kind of a pain in the ass, but I don't know. So there it is. That's the format. So all your components are there. You got your vertices, your triangle faces, your UVs, weights, and stuff like that. So yeah, the format honestly is very well understood. The unknowns that I did have were silly, like constants, which they're always going to be the same, so it's not much of a problem there. So the constants that we usually see are that one value or zeros, so that they could even be padding, so that's not a big problem. So yeah, that's the UX format. Very well understood, easy to understand. Now the problem comes in at the last data section. Okay, and that's the what's it called, POF or poop. I don't know. This thing here. All right. Now I don't want to take up too much time, so I'm just going to go through this kind of quickly. This is the main reason why we can't write geometry back, because without this working, it will crash the game, and we don't know why. We just know it's here, and it's annoying. So first off, you can see there's a bunch of 43s and 41s. I don't know why it does that. So what I did is I XOR'd by 43. I'm not saying this is right, but I did this to kind of help me visualize what's going on here. So beyond that, you can see there's still these 2's that keep repeating. So I again went back and I XOR'd by 2. And then I got that, which was lame. So let's go back here. Let's just XOR this. Yeah. Alright, so that's XOR'd. And we'll XOR that. And that. And so forth and so forth. Okay. So, let's look at this thing. Actually, I don't think I was supposed to XOR that. That was the chunk header. Yeah, that's a chunk header. That was understood already. Then this thing looks like a size of some sort, which doesn't make sense because in little endian it's 516, which doesn't really correlate with anything. Let me look at this table here. If I shrink it down, this table's not too difficult. Let me just cut it off here so you can see it. Alright, so these are the entries, and the entries correlate directly with the sub-object count, which was 2a, which is 42, so there's going to be 42 of these entries. The first entry is always 41, and then the ones in the list go 20. Alright, so these are, so this is 1, 2, 3, 4, 5, so 5, so 2a, and I'm just going to jump 5 times. 1, 2, 3, 4, 5. Wait, what am I doing? That was the wrong thing, bro. 1, 2, 3, 4, 5. Yeah, I put B4. Knob, okay. 1. No, what am I doing? No. 2A. I want 2A in there, yeah. What the fuck am I doing? 2A. Yes, okay. So starting from this position, 1, 2, 3, 4, 5. And that, well, that doesn't look right. Maybe I'm supposed to be from here. That doesn't make any sense. 1, 2, 3, 4, 5. Yeah. The fuck, now it works out. Okay, so yeah, now we should be here. Somehow. Don't remember how. So yeah, this stuff you can pretty much parse pretty easy, because it's the sub-object count times this and it's constant, so that's not a problem. This 6 is a problem. Remember in the header, there's an unknown up there. It says 0606. Depending on that value or integer, sometimes it's 6, sometimes it's 4. That will change the type of data that shows up in here. So based on a type 6, which seems to be always the first object, oh my god, it's so difficult. Alright, so based off, I don't know, why do I got this like this? Expand that shit, thank you. Alright, so based off of that table, we're now sitting where? Right here. Alright, so this seems to be a different size based on the count. So it says 6 up there, so we have a type 6 up here. That has a certain size to it, which I still haven't figured out. And then there's a float value here, I believe. I'm not sure why, so that's a float value. And then there's a bunch of zeros. So if you remember, the strip count for our first object was 81. The second one, what is the second one? Let's see here, B4. Okay, so this one's 81, that one's 8A. So we'll just go back up here. So this one, after the float value, you jump 8, 1, so that's how many strips were in the first sub-object. And that lands you roughly around this integer value. And then after that, it's again similar to like up here where it was 6 something something. This one's 1a and then something something something. Then leads up to another float value. Okay, and then again we're going to jump 8a this time. That's the second sub-object strip count for position. And again, that leads us past this integer value, and then again that structure, like we had the 6 at the beginning. This one's 2D at the beginning, and then leads us to another float value. So the float values, oddly enough, are pretty much close in range. This one says 113 as a float value. This one's 111 as a float value. This one is the same, it's identical. So I don't know. I have no idea how to. Okay, I'll put it this way. I can see patterns here. I don't know what the hell the values mean. I don't know what the hell the mystery data is. So to summarize it, I don't know what the hell is going on in here. And the only thing I know is this thing needs to be correctly written for there to be new models in the game. And another thing is they friggin' did something like they tried to hide the data values by doing some bullshit here. So I'm not sure if this is a security mechanism they put in place or what. It's either dumb or genius. I'm not sure what it is. But anyway, I think I should leave off there. I took up a lot of time. That is the UX binary format that they use for Rumble Roses XX. I probably won't get the structures up tonight. I'll do it maybe on the weekend or whatever when I'm not so tired. But I'll put those structures up for you guys if you guys are interested in programming. Yeah, if you guys can figure out that last section, I guarantee you'll be able to make a model importer of some type. But that's yet to be seen, I suppose. Anyway, hopefully that opened your mind, and thank you for watching, guys. You have a good one. All right, bye.